And welcome to Module 4, ACL Concepts. So this one's not too bad as far as death by PowerPoint, but it's still a lot of theory. So we'll be explaining how we filter traffic using ACLs, which is access control lists, and how wildcard masks work in relation to ACLs. Then we'll go through the basic principles on creating ACLs and then have a look at the standard and extended ACLs for IP version 4. So what are they? They're a set of commands that are used to filter traffic. Now, the purpose of these control lists are to permit or deny traffic based on a set of conditions that are set out line by line within the ACL. And how this works is as the traffic enters an interface that has an ACL active, it will compare the headers of the traffic to its conditional programs. So the way it does this is via sequential order. So first line, second line, third line, fourth line, until it finds a match. If it gets a match, it does whatever has been the action associated with that match. So these are the permit, in other words, allow the traffic to go through, or deny, drop the packet. So why do we want to use them? Well, we can limit traffic, which will increase network performance, especially over slower links. We can also provide flow control. We can provide security for network access. We can filter traffic based on traffic types. We can screen individual hosts or a range of hosts from certain network services. And we can give priority values to network traffic types. So all of these are available functions by ACLs. Now, as you move further into your studies, CCNA is only going to be your start of your journey. So when you get into the more advanced material, you'll see that these control lists are used for so many different things within routing. We do filtering of traffic, we do filtering of route distribution, we can do all sorts of interesting things with these control lists. So packet filtering generally works at layer 3 and layer 4, depending on which of the options you use. So in a standard ACL, we only filter on IP addresses. Okay, so that's only going to work at layer 3. With the extended ACLs, we expand that to include the ports for TCP, UDP, and different protocol types can also be used within the filtering process. So this expands into a wider category of options, and we can fine-tune the list to do specific tasks. So standard's pretty much a brute force, whereas extended is very much a fine-tuning instrument. So how does it work? Well, we have two types of traffic. We have inbound and outbound, and we can filter on either of these conditions. So we can place a ACL on an interface and we tell it which way to monitor the traffic. So we put it on, for example, Fast Ethernet 01, and we say it's going to filter it based on inbound traffic. So that's the only traffic it's going to monitor. Okay, so outbound traffic through that interface doesn't go through the ACL. It's not checked. It's just mosey on through. Inbound traffic will be scrutinied to find a match in the conditional ACL and handled appropriately based on the rules set out in the ACL. So basically the packet arrives at the interface, it's picked up, and the router extracts the header information from the packet, which is your IPv4 addresses. It then starts at the top of the ACL and compares each conditional line in sequential order until it finds a match. Once that match is made, it carries out the instruction that was attached to that line. Now that can be a permit or a deny statement, and the remaining conditions aren't checked. So once a match has occurred, that action is taken. No other statement is compared. If there is no matches within the lines of the ACL, there is an automatic statement that is not shown when you view an ACL, but it's an explicit deny statement, which means if there's no other match, the packet's discarded. Okay? So when you write an ACL, you must at least have one permit statement, or you've just effectively blocked that interface. Because if there's no permit statements to permit traffic, everything's denied. Okay, wildcard masks. These are a little different. Okay, so when you're laying out your wildcard mask with an ACL, the 0 bit is used to represent a bit that has to match your condition. A 1 means it's ignored. Okay, so how this works is a very simple rule that compares a source. When you write these lines, they must have something to compare against. So as we're comparing IP addresses, you'll put in an IP address and then you'll put in a wildcard mask stating which bits of that source condition needs to be matched bit by bit. Now, what's a little bit different with these conditional statements is, unlike subnets and addressing that we've all done up until now, you do not have to have contiguous zeros and then ones. Okay, so with OSPF, if it was a /24, you'd have 24 zeros and then 8 ones in its wildcard mask. This is not subnetting. This is control lists. So what you do is you stipulate which bit is to be matched with your original address and which bits can be ignored. Now they don't have to be sequential. You get to pick and choose which bits are matched and which ones are ignored. This gives you a great flexibility of arranging for a range of addresses that can match a statement. So, when we put it out, as I said, a 0 is a match. So, if, for example here, we have 8 zeros in the last octet, that means all the bits in the last octet need to match. Okay, so if you look at the example here, we have all zeros across the range. That means each of these octets have to match exactly what's in our example. Next one down is a /63. So if you expand that out, it's a 0, 0, quad 1. Alright, so first 3 octets have to match because they're zeros, and the last 2 bits to be matched are the first 2 in the last octet. The last 6 bits doesn't have to match, so they can be ignored. Doesn't take their values into account. So as you look through this list, you'll see that the example here, we have first 3 octets need to be matched. Then it's a 248, which means we can ignore the first 6 bits of the last octet, but the last 2 bits of that octet have to match. As I said, it does not have to be consecutive. It is purely a bit by bit matching task. So you determine which one is matched and which one's ignored, and as I said before, they do not have to be grouped all zeros or ones. This is taken bit by bit. So the way it looks is you make a statement. So in here we are going to say that ACL 10 needs to only permit hosts with IP addresses of 192.168.1.1. Okay, so it's a single host. So the wildcard mask is 0000. So when a packet arrives on the interface, that this is active one, it looks at the address and it will pull it out and check, okay, does this bit match this bit? Alright, so this is the traffic, so it's got to match. Yes it does, yes it does, yes it does. And it does this check all the way down, and all 32 bits match, so therefore it does the action resulting from that line, which is permit. So this traffic is allowed to continue its journey through the interface. Okay, in this example, we're permitting the hosts within the 192.168.1 network. So the wildcard mask is 000255. So it only has to match the first 3 octets, or the first 24 bits, and it's going to ignore every bit in the last octet. So it doesn't matter what combination is in this last octet, as long as these 24 bits match, it'll be permitted through the interface. Now, the examples we're looking at is a standard ACL, and it only checks the source IP address of the packet. So here we want to permit the hosts from a range of networks from 192.168.16 through to 192.168.31. So you need to look at a combination of bits that changes. So what bit changes between 16 and 31? So if you look at our IP address, there's our 16, so that's common across all of that range, because 31, would these all be turned on? Yes, they would, because that's the combination there. But when we go to 32, all of these will be turned off, and that one would be on. So if we want to match that range, we only need to check the 16, because if it's going to be above 16, it's a match to our statement. If it's less than 32, okay, so if it's below 16, the 16th value won't be on. It'd be an 8, a 4, a 2, or 1, which means it could only be a total of 15. So if we match the 0001, that means it's going to be at least 16. If we add any combos behind that, that'll only take it up to 31. So we don't need to check any of those. And we don't need to check any of the last octet, because they're the hosts we want them to permitted to go through. So this is where knowing how to do your IP addressing via binary by hand comes into play, because when you start doing ACLs, you need to put your ACLs laid out in binary and look at the binary bits to work out your filtering. So if you're doing everything with calculators and that, this is where you're going to start to have issues working out your filtering patterns. Okay, so if it's a straight subnet you wish to permit, the wildcard mask can be calculated just like we did with OSPF. Okay, you could just subtract it from 255, 255, 255, 255 and subtract the subnet mask, and you would get the corresponding wildcard mask for the entire subnet. That still works. It's only when you need to start filtering ranges or tricky things that you need to break it down. Now, ACLs have a couple of keywords, which are host and any. So the host keyword can be substituted for any quad 0 mask. So in other words, it's only filtering for a specific device, a single address. Any substitutes the mask of 255, 255, 255, 255. So in other words, when you want any address to go through, because you're ignoring all the bits. Alright, so each interface is capable of supporting an inbound and an outbound filter. Now, if you're running both IPv4 and v6, you can have 4 filters, an inbound and outbound for each protocol. And of course, there's other protocols other than IP out there, so they're available for you to work with as well. So with ACLs, we need to take great care, because if we make a mistake, we upset the traffic plans that we're trying to make. So you need to make sure when you go to create these filters that you are meeting guidelines and policies set out in the security policies. You want to write out your ACLs in English or your language first. In other words, you need to have a clear understanding of what the function of the ACL is. Okay? You need to use text editors to create, edit, and save your ACLs. Now, you do this so that it's easier to edit in the long term. When you do a change to a null ACL, you need to delete whatever's there first and then put the new ACL in. So by using a text editor and then using the cut and paste function, you can quickly edit and reapply any ACLs you wish to. It's always best to use a remark in your ACLs, and these remarks help explain what you're doing or the function of the ACL, because these can be months or years between being edited, so you may have forgotten exactly what the ACL's purpose was between changes, or maybe a different tech that comes in and makes the changes. So as with programming, it's always good to comment on your programming, and the same with your ACLs. Always try to test your ACLs before you put them into a production network. Try to avoid doing your testing and learning in a live network, as in a production network. It doesn't end well. Standard ACLs permit and deny traffic based on their source IP address. Extended do the same, but they can also use the source and destination IP addresses, as well as the source and destination port numbers. So extended ACLs are a much more powerful filter and require a lot more information to be able to filter the traffic. So if you just do access list and a question mark in the command, you'll get a range of numbers, and they'll tell you whether it's a standard, extended, whether it's a MAC address. There's a whole range of them. And these have been slightly changed and modified, and as you can see there, it's not the entire list. Okay, some of these ranges and that are used for other protocols that are not covered in this chapter. So as I said, we're only looking at IP traffic. So these are the ranges that you need to understand. So let's have a look at the filter. So in this one we're looking at a named ACL compared to a numbered ACL. Now the difference is a named ACL can actually be edited within the device. You can add lines to it, insert lines. With the named ACLs, we can also do some other dynamic filtering techniques for firewalls and things like that. So a named ACL is quite a powerful tool, and it opens up many other options over those of a numbered ACL. So in this example we have an IP access list that is extended with a name of FTP-FILTER. The first line that is going to be looked at is it's going to filter based on the source being TCP traffic from 192.168.10.0 network, because the wildcard mask is only looking at the first 3 octets, going to any destination equal to the FTP protocol. The second line is the same, but it's looking for access at the destination for FTP data. So what we're doing here at the end is putting operands on. So what we're saying is we're going to any IP address, but it must equal the FTP protocol port. Okay, this one's saying it's got to be equal to the FTP data port, and these are port 20 and 21 if I remember correctly off the top of my head. It's been a while since I've looked at the ACL port number list. Okay, so where do we place ACLs? It's very simple. If it's a standard ACL, we place it as close to the destination as possible because it only filters on the source. So standard equals as close to the end as we can get it. Extended, as close to the source as we can get it. Now, the reason behind this logic. With a standard ACL, we're only filtering traffic based on the source IP address. So if we put it close to the source, we won't gain access to any of the other destinations that are valid, because it's not looking at where the traffic flows, it's only looking at that point. So we need to control what we're going to do with it. Whereas an extended ACL, we specify the source, the destination, the protocol, the ports, so we have very distinct control over the traffic, and only exact matches to that will be filtered. So we can put that as close to the source as we can. That way we save all these intermediate network resources from processing any traffic that is eventually going to be dropped. So let's remember, when we say close to the source or close to the destination as we can, it's within our organization. We can't obviously put filters in another person's network or another organization network. We may want to filter our unwanted traffic so that we can save bandwidth. Alright. Traditionally, WAN links are slow, up to 2 megabits, so we don't want traffic that's going to be filtered traveling across those links. It's much easier to knock them out as soon as possible. We need to consider our configuration requirements and choose the appropriate ACL based on what we're trying to achieve. Sometimes the simplest solution is to use a standard ACL rather than an extended. Excuse me. But you need to make that choice based on your conditions that you need to filter. So in here, we're doing a standard ACL placement, so we want to filter it as close to the destination. Okay, so we want to prevent traffic originating from the 10 network, so this one here, from getting to the 30 network, which is this one here. So if we place it on the inbound of S011, we're stopping it from getting to both the 30 and 31, which is not what we want. Whereas if we place it as close to the destination, which is the outbound of G000, then the traffic has access to all the networks except for 30, which is what the condition is met. So that's basically going through what I just talked about. Now, with an extended ACL, in this one, we want to deny telnet traffic and FTP traffic to companies B's 30 network from the 11 network. So we want to filter traffic from this network from entering this network. Now, because we're using an extended, we can specify the source and the destination. So we can put it in 2 locations. We can filter it here as an inbound on G001, or we can filter it as an outbound on S010. Now, there's benefits to putting it on the serial link over the inbound here. Reason is we're not affecting or slowing down traffic that is travelling from 11 to 10. We're only going to start filtering the traffic that's going across the WAN link, and this traffic must travel across the WAN link to get to our destination. So we can have it there and be effective, or we can have it there. Choice is yours, but comes down to what you want. Now, if you're a stickler for the rule, G00 is the closest source, but as I said, you're also stopping and filtering traffic that is jumping from the .11 to the .10 network. Now, depending on the amount of traffic flow, you may not want that filter to have a look at that. So that's the more logical place for it. So that's a quick look on what filters are and how we come about to putting them in place. So you're now aware that access control lists are available to put on interfaces, and their function is to filter traffic based on a condition set out in the rules. There are standard and extended ACLs, as well as numbered and named ACLs. When we use the numbered ACLs, the number that we use tells the device whether it's a standard or extended. With the wildcard masks, we are telling it to determine which bit to match and which bit to ignore. Now this is based on its entire 32-bit range, but it matches based on a bit-by-bit process. So as it's going through, it is only going to look at a bit at a time. As soon as it doesn't get a match, it stops comparing those bits and goes on to the next line. We then had a look at the two keywords that you can use within the ACL, which is the host and any, which replace the quad 0 and quad 255 wildcard masks. When we go into the actual configuration, which is in the next chapter, we'll see that we have to have them in specific placement for them to take effect. Each ACL can be placed in either an inbound or an outbound position on an interface. So we can have 2 active filters per interface per protocol. Standard ACLs only look at the source IP address. Extended ACLs look at the source address, destination address, protocol types, and ports, so our applications. Now this filtering can be both done on the source and destination of any of those. So we can specify the source protocol, the source port number, and as well as the destinations. Don't fall into the trap that we can only filter on the destination ports. We can also filter on the source ports. Named ACLs are the preferred method or best practice because, as I said, they allow us the most flexibility coming to making changes, and they also allow us to create dynamic ACLs later on. Not in the scope of this chapter. When you place your ACLs, the rules are, rule of thumb, standard as close to the source, extended close to the destination. Is that right? No. Just seeing if anybody's still awake at the end of the video. Alright. Standard, close to the destination, extended, close to the source, but use some little bit of common sense in the placement of these to minimize the impact on the traffic flow. Remember, every time we inspect a packet, we increase the delay. So if we don't need to force traffic through a filter, we can place it somewhere else without affecting the overall conditions that we need to meet and increase efficiency of traffic flow to other areas of the network that would not be impacted by the ACL. Then use that one. The example was the extended ACL where we could have put it on the inbound interface or the outbound interface. Both do the same job, meet the conditions, but placing it on the outbound interface allowed natural flow at the greatest speed with the least amount of delay between the two networks directly connected on the same device. So that brings us to the end of this chapter. Reminder that the next one is hands-on. It's where we actually do the calculations and go through many examples on the actual configuration. So I hope you join us for that one. Until then, good day to you. Happy reading, because it's a very dry chapter. But the next one gets a little bit more interesting as we get to actually configure these and see them in work and practice. Until then, goodbye.